Okay, welcome Genevieve and Heather and Sammy to the week 10 webinar. And I want to mention a couple things and then I'll share my desktop. First, the main thing is you just finished your exam, whether that was Thursday or Saturday or Sunday. And so that means it's my turn. So I'm grading it, but it doesn't like suddenly get graded. It takes a lot of work for me. So I've finished grading the Thursday version. I've finished grading the Saturday version. I think I'm one problem into the Sunday version. And I'm teaching now and I'm teaching in a little bit. So today's kind of a busy day. I don't expect to finish today. But tomorrow's an easy day. So I should have everything completely finished by tomorrow. That's my goal. And I'm pretty sure that'll happen. So your exam should be graded by tomorrow. And, it's possible I might even throw some curve points in there. So even if you think you know what you got, it could even go up a little bit. Again, I have to grade the whole thing first. So again, my plan is to finish grading tomorrow. And I want to mention the big thing coming up this week is, hopefully you all know.
Project 2.
Yeah, Project 2. So you should be deeply involved in Project 2 at this point, because if you want me to read it, and I strongly suggest you wanting me to read it before you turn it in, so you can get feedback. That has to be done by 8 a.m. on Thursday. But if you send it 8 a.m. on Thursday, it might take me a while to get back to you because reading a bunch of 8-page projects takes a long time. It doesn't just happen in 5 minutes. So I read them on a first come, first read basis. So if you send it, Wednesday morning, then you'll probably get it back by Wednesday without any issue. If you send it at 7:59 a.m. on Thursday, it might take me a while because then you're last in line. So that's just a note, a major thing you just finished, and then the major thing that's coming up. So this is kind of a big time in the course when it comes to big pieces. So let me share my desktop and talk about the plan today. Okay, so here's the plan. As always, I'm always happy to answer questions, and I'll do that as soon as we get through the plan. And then we're going into chapter 11. Chapter 11 is a very unique chapter in that pretty much this whole course, I don't know if you realize, but we've been focusing on quantitative survey questions and yes/no questions. Isn't that right? So that, or quantitative data and yes/no data. Is there other kind of data? What do you think? Or is that all there is? Either there's a number or a yes/no. What do you think?
What about those kind of data where it says like 1, 2, 3, 4, 5, or like the happy faces, like good,
Okay,
bad?
1, 2, 3, 4, 5 is quantitative because those are numbers, right?
Yeah. Yes.
But if it was like happy face, sad face, and I don't know, kind of blank face, that is a different kind, and that's what we're doing now. And that's qualitative, not yes/no. Okay, so hello.
Yes.
Oh, my screen just went black. Did you see anything weird?
Your face is frozen.
Everyone there? My face is frozen. Sorry about that. I have no idea what happened. My screen went black, but you can hear me, right?
We can see your screen still.
Okay, good. Just want to make sure. I've never seen that screen go black before, and it took about 2 seconds. So yeah, so if something happens, then you know what happened. Something technology happened. That was weird. But anyway, we're going to be dealing with the qualitative, not yes/no type questions. So that could be, type of face. It could be What is your ethnicity? That's a very typical qualitative question. You can't put a number to that. Doesn't make any sense. It's not yes or no. And it's important. It's something that comes up a lot. And there's a lot of other types. What's your favorite color? Okay. You can do quantitative, but my guess, and maybe I'm wrong, any of you know that why that's quantitative, except that most people don't think of it that way? And my guess is you don't, but if you happen to understand quantum physics and there's a spectrum analysis, that we're not doing that. We're going to be thinking, regular, and that is blue, red, bunch of words, not numbers, not yes, no. But there are a lot of different surveys where you're looking at qualitative. Another way might be the Likert scale. Do you remember what that is? Remember? That's the strongly disagree, agree, and strongly agree. You've seen those kind of surveys. And again, it's not yes or no. It's not a number. It's a word. So we're going to be dealing with word answers mostly, okay, where you have not anything that we've been able to do before. So it's going to be a lot different than what we've seen before. The other good news is that most people consider this one of the easier chapters in the book. So this is an easy week in terms of the material, but your projects are due, so you still have a lot to do. So that's one reason why I let it go a little light for this week. It's also mostly done for research. You'll very rarely see this kind of stuff in day-to-day life. It's more for research papers. So I'm not able to find a news article that talks about what we're going to be doing because it's research. So we're going to do 3 types. One is called goodness of fit. And that turns out to be when you are wanting to see if a distribution fits an expected distribution. And we'll see what that means with examples. And then we'll get into a test for homogeneity. And that has to do when you're comparing 2 different groups and seeing if their qualitative answers are the same as each other's. And that's a test for homogeneity. And then finally, we're going to do a test for independence. And that's where you want to see, is this question independent of another question's answer? Okay, so for example, race and major, are those independent of each other? Or are they dependent? Does it make a difference? So that's the different types of analysis we're going to be doing. All of these use a distribution we have not seen before. So we've seen a lot of distributions. See if you can talk in the chat box to say what the distributions we've had in this class so far. There's the biggie that you should all know, like yeah, uniform's one of them. That's not the biggie, but that one's important. What others have we had? Yeah, normal is another one. That's the biggie. So normal distribution is a big one that comes up in a huge way because of central limit theorem. We've had some others too. We've had 2 others, I believe, so far. Okay, and if you don't remember, that's okay. There's a binomial distribution. Do you remember that happened with the yes, no question number of trials? And then there was also, we had the t distribution. And that comes up when you're doing a hypothesis test for a mean and you don't know the standard deviation of the population. So you use the t distribution. And today, all of these tests that we're working with today have a different distribution called the chi-squared distribution. So we're going to be working on the chi-squared tests. So all of these are chi-squared tests. But if I ask you the test, don't just say chi-squared. Either say chi-squared good as a fit, chi-squared homogeneity, or chi-squared independence. So that is the plan. That is the plan of the day. Are there any questions at all on anything? Okay, if there's no questions, then I can move on. And today might be a shorter day, by the way. And if you don't like that, you can always ask questions and it'll go longer. It might be shorter because, again, we have a little less to do today. This is not one of the harder chapters, but you got a project due this week. So you got plenty to do. It's not like it's a light week. It's just a light topics week. So I'm going to do these by example. I think that's really the best way of getting a feel for all this. Okay, so I have my first example here. And that is the racial distribution of students at Lake Tahoe Community College the same as it is for South Lake Tahoe, the town we live in? Okay, the town the college is in. Right? What do you think? Do you think it's the same? Okay. And again, we'll find out, although I want to give you a big disclaimer. I made all these numbers up when it comes to the survey. A survey could have been done of students, but I didn't have time this morning to ask 200 students. So I made up numbers. So hopefully you'll understand. But I want to let you know that this could be done. On the other hand, these percents, 63%, 26%, 6%, and 5%, that I got, I think, on the El Dorado County Census Bureau webpage. So that's actually, that you can quote me on. So the racial distribution of South Lake Tahoe is 63% white, 26% Hispanic, 6% Asian, and 5% other races. Okay. And again, that's just a known percent because they take a census and that's what's given and found online. It was easy to find. Okay. On the other hand, a survey, which wouldn't have been easy if I did it in reality, but it can be done. A survey of 200 students found 114 white, 62 Hispanic, 10 Asian, and 14 other. Okay, what can be concluded at the 5% level of significance? Any questions on the question? Okay, does this fit in with any of the examples or techniques that we've had so far in class? Like, can you do a hypothesis test for a proportion? Would that work for this? You know, would anything work? Any thoughts? Hypothesis test for data. So when we talk about a hypothesis test, it's usually data, but what kind of data? Are we talking means, proportions? What are you talking about? Because that's what we've had. We've compared two means. We've looked at a single mean. We've compared two proportions. We've looked at a single proportion. That's what we've had so far. So any thoughts? Have we done anything like this? Okay. The answer is not quite. Okay. Although you could look at it this way, and I want to see if you can come up with a problem with it. You could say, well, we could do the hypothesis that, notice there were 200 students, 114 were white, right? You could do a hypothesis, is that 63%? Right? To compare with the whites. And then you can do another hypothesis test for Hispanics and say that the 62 is that 26%, right? You could do H naught P equals 0.26. And then you could do the Asians, same idea, and you can compare with 6%. And then you could do the others and compare with 5%. So you could do 4 different hypothesis tests. And if any of those end up rejecting the null hypothesis, then you say, hey, we have different proportions. Does everyone understand that idea? Okay, here's a harder question. What's wrong with it? And there's definitely something wrong with it. Anyone see the problem?
I see that the 6% Asian is 10, but the 5% is 14. Does that mess the hypothesis testing up? Just, I mean, isn't 5% lower than 6%?
Right. So that would say that you'd probably reject the null hypothesis, right? So that's not statistic. It doesn't mean that you can't do it. It just means you might end up rejecting the null hypothesis. Do you see? That's what you're trying to look
Okay.
at, right?
Yeah.
These numbers aren't going to be the same as the percents because we have a sample. Whenever you have a sample, things are going to vary a bit. And the big question is, are they varying more than they should? Does that make sense?
Yeah.
So here, this 14, by the way, is 7%. So we're 2% higher than we are supposed to be, right? Was 2% a lot or a little? And that hypothesis tests are all about that. P-values are for that, right? So we could find a p-value for that. But what's the problem? There is a problem. There is a problem with doing 4 hypothesis tests. And then if one of them fails, or if one of them rejects the null hypothesis, and you say that, no, they're not the same. What's the issue? Let's see. Okay, I think I better tell you because usually people don't guess, and it has to do with the probability of a type 1 error. So if we use 5% for your standard level of significance, then what's going to end up happening is that for each of these tests, if the distribution is the same, then there's going to be a 5% chance of a type 1 error. Well, guess what? We're doing 4 different tests. And if you do 4 different tests and there's a 5% chance of a type 1 error for each of them, all of a sudden you're close to a 20% chance of a type 1 error. Do you see the problem? So there's some issues about trying to do these one at a time. And we don't do it that way, because if you do it that way, you come up with bad issues. And you can kind of adjust, but the math is actually kind of tough to do that. Instead, you let the old mathematicians adjust for you, and that's what they've done. And we're going to do what's called a chi-squared goodness of fit test. Let me write this out. And let me write down the symbols too, because it's good to know. So chi-squared, chi is a letter. It's a Greek letter. It's one that you may not have seen before. It's not like pi where everyone's seen it. And it's that one right there. So that's called a chi. And it's chi-squared. So it's a chi-squared goodness of fit test. Okay, and a chi-squared goodness of fit test, what it does is it tests to see whether you fit a given or a known distribution. So it tests to see whether or not a distribution or a sample, actually I should say a population, fits a known distribution. So we know the distribution, the ethnic distribution of South Lake Tahoe. That's known, right? Census Bureau, they've asked everyone, okay, if they've done their job right. Okay, and in fact, this year, and this is actually the hardest of my lifetime. This is the census year. Do y'all know that? So, and they're supposed to have been done. Okay, I guess last year was the official census year. And this is the first time in my lifetime that they couldn't get it done. And hopefully you all know why. Why they needed it, why it's taken an extra year. Okay, and if you don't, then I don't know where you've been. And that is, surveying people is really hard. Okay, it's so much harder to do statistics now than it was a year ago. And that's because of COVID. So the census is taking longer than it usually takes, because normally by now it's done. But again, these are census numbers, 62%, 63%, 26%. Those are known numbers for the entire population. What we don't know is LTCC. Okay, so that's why you have your sample, and you're going to use your sample to see if it fits an expected distribution. Any questions on that idea? Okay, now you should be used to the first step in any hypothesis test. Which is? Yeah, H0 and H1. All right, now this is something that's a little dangerous actually, because I'm going to be doing something that's very different than what we've done before. And what's dangerous is if I give you a test question that involves a hypothesis test that comes from chapter 9 or chapter 10, you need to still do it the way we did it in chapter 9 and 10. Got it? And that was how many words if it was a chapter 9 and 10 or an H0? When I say write down the null hypothesis, how many words are in there? Not one. That's too many. 0. It's all symbols. It's like P equals 0.3 or mu equals 7. Remember that? Or P1 equals P2. Okay. No words. So on the final exam, if you have words in your H0, I will take off points. Okay. And same thing with the H1 if it's coming from chapters 9 or 10. Got it? Okay. And I want to let you know, some of you didn't put symbols down when I asked you on the exam. And yeah, I took off points because you're supposed to have it in symbols. That's what H0 and H1 are. Every example I've given has H0 and H1. The homework problems have H0 and H1 with symbols. Okay. On the other hand, in chapter 11, it's all words, no symbols. So again, that's not a problem. What the problem is remembering that it was all symbols, no words for the earlier chapters. Because for some reason people start wanting to do words again. Okay, so H0 is the following. The distribution. Okay, and maybe even the racial distribution of students at LTCC is the same as the racial distribution in South Lake Tahoe. Any questions on that? Oops, let's spell it right. I want to highlight this word right here, distribution. Okay, if I ask you to do a goodness of fit test and you don't have the word distribution in your H0, you will lose points, guaranteed. And the good news is, if I ask you, if you do a goodness of fit test and you have the word distribution in, you get points. Even if the rest is nonsense, at least you have the word distribution and I'll give you a point or two. Okay. So again, that's a big piece. It's a big piece of this because goodness of fit tests whether or not the distribution of the unknown is the same as the distribution of the known. So in this case, LTCC is the unknown and South Lake Tahoe is a known. Any questions at all on the idea of the H0? Okay, well, I got H0, so now I need You better all know. Next step. It's not a trick question. Yeah, H1. Okay, and the nice thing, especially the nice thing since I'm actually typing this, and by the way, in your final, you're gonna be typing also. So, and also your, so your final type also. So I can copy paste. And what changes? And all I do is add one word in. What word do I put in and where?
Would you be different instead of same? Just add not the same or different.
Yeah, you could do either different, but for typing reasons is not. Very easy. Okay, if you could also write the distribution of students at LTC is different from the racial distribution in South Lake Tahoe. And that's fine, more typing, but you can do that if you want to. It's totally up to you. Any questions at all on H0 and H1? Any questions? Okay, now comes the next step. And the next step, a lot of people have trouble with. So, pay attention here because this could sometimes be the hard part. And that is we need to look at the numbers. And we need to organize the numbers better than they are as they're written in a paragraph. And the way we do that is we're going to make a table of observed and expected values. So I am going to go insert table. Like so. And you can make it horizontal, you can make it vertical, that's up to you. Just to fit on the page nicely, I made it horizontal. And I'm going to write O for observed and E for expected. That's standard. So the observed are really easy because if you look at the observed, all you do is you write down what was observed. Okay. And if you want, some people will do this, so maybe I'll do that too. Let's we can write down so we can keep track. We have our white, we have our Hispanic, we have our Asian, and we have our other. Just it makes it easier to read, maybe. Not necessary, but a little easier. So for the observed, how many whites did we observe? Yeah, 114. Okay, this is just a matter of reading and putting in the numbers. 62 for Hispanics. And then the Asians, 10. The others were 14. Any questions on the first row of the table, the observed row? Okay, for the expected, now we have to say how many would we expect if H0 is true? Okay, H0 being true is that the racial distribution is the same as what it is in South Lake Tahoe. And the idea is 63% of residents of South Lake Tahoe are white. We surveyed 200 people. Well, how would we find out how many whites would we expect?
By taking the demographics of whites in El Dorado County, right? Or in South Lake Tahoe?
In South Lake Tahoe, yeah. Yeah, so we're going to do not 114 divided by 200, because remember, these are expected. Expected happens before you even take your sample. What you expect to happen before you start. And the idea, we expect 63% to be white, and we're going to do a sample of 200 students. So we just take 63% of 200. Or 0.63 times 200, which is 126. Anyone lost in what I just did?
Can you go over that one more time? You would
Okay.
times
63%,
0.63. Okay.
which is 0.63 times the sample size, which was 200. So if there really were 63% whites, we would expect 63% of the 200 to be white. By the way, did we get the expected to be the same as the observed? No, we didn't. Does that mean that the Lake Tahoe Community College is not the same?
No, because you only surveyed 200 people.
Exactly. We only have a sample. When you have a sample, we don't know it until we compute a p-value. So right now, yeah, it's different, but we expect it to be a little different. We don't expect it to be a lot different. If it's a lot different, we're going to have a really small p-value. If it's a little different, then your p-value won't be small. Okay, for all of these, and there's going to be some kind of weird combining that we don't have to worry about, but the math is tough, by the way. Okay, so we do the same thing. 26% of 200 is 52. 6% of 200 is 12. And 5% of 200 is 10. Anyone lost on that basic arithmetic?
Can you just scroll down a little bit, please?
Sure. Yeah, it's always hard because I wanted to be able to read the givens put in. So there's our observed and there's our expected. Any questions on this? Okay, what's typically the next thing you do? We're hypothesis testing. Usually you'll think about level of significance, right? And this is a demographic question. So use standard, 5% sounds about right. Whenever you have sociological, demographic type stuff, it's almost 5%. Okay. And no one's going to give you the level of significance on these things typically. But if you needed to, that's what you do. And then you go find the p-value, right? So the good news is you don't have to do the math to find the p-value. You just have to go to the calculator. And by the way, we're towards the end of the class. I don't know if you figured that out yet. So we're getting down there on the calculator. You notice that? We're getting low. Okay, what do you think this one is? Yeah, it's 21, goodness of fit, because I told you that's called a goodness of fit test. Okay, and what the instructions say is type in the values from the observed and expected separated by commas. So our observed were 114, 62, 10, and 14. Our expected were 126, 52, 12, and 10. That was given in the tables. Any questions so far? And I hit calculate. Oh, wait, I forgot the comma. Yeah, that'll do it. Let's try again. Much better. Okay, so notice it gives you chi-squared, that's how you read this, is about 5. And that's a test statistic. Okay, again, chi-squared is, it's a distribution. So that's the value on the x-axis that you put. And then everything to the right of that value, the area to the right is the p-value. Right? That's how this class works, right? So the p-value is 0.1718 about, right? Maybe 0.1719. What's the conclusion if that's our p-value? At this point in class, you better all know what to do when your p-value is around 0.17.
Gotta fail to reject.
We fail to reject. Yeah, that's a large p-value. Okay, even if they didn't give you level significance, that's a large p-value. So I'm going to go back and note that our test statistic was about 5. Our p-value was equal to 0.17-ish, which is certainly greater than 0.05 by a lot. So now we can say there is statistically insignificant evidence. Okay, at this point, these words that I just wrote down, it should be in your brains, because we've been doing this for weeks now. Okay, and it doesn't go away. It keeps going the next couple of weeks too. So there's statistically insignificant evidence and I like to do, when it's insignificance, I like to use a whether or not to decide whether or not. Okay, and that's only when it's insignificant to do whether or not. And then, because I'm typing, I can pick either of those if I say whether or not. That's the good news. So I can copy this guy. I can paste it. Take that T and make it lowercase. The racial distribution. And there's no reason to make that red. Of students at LTCC is the same as the racial distribution in South Lake Tahoe. Okay. If there's a large p-value, we automatically assume. Actually, if there's a large p-value, you don't have to assume anything on the level of significance, like on this example. You put your favorite p-value in, and it's the same inequality. If I use 0.1, it still works. Do you see? If I use 0.01, it still works. Okay, it's still large and it's still greater than, and there's still statistically insignificant evidence. Okay, if the p-value is like borderline, like 0.06, then you got to think about it. Then you might say there's only weak evidence or something like that. Okay, but when you have 0.17, it's cut and dry. It's insignificant. Any questions on that? And that's it. We're done.
Can you just scroll up a little bit
Sure.
so I can write that?
Now, I want to mention something that's very important, and that is this is all we can say. Okay? We don't know whether it is or isn't. We don't know, if we did have evidence, we wouldn't be able to say which is the one that is different, white, Hispanic, Asian, or other. You can't talk about that. Okay? That doesn't mean it can't be done. It just can't be done in our class. So if you want to learn about how it can be done, what do you have to do? If you want to learn how to go further and figure out which ones are different instead of is it different? Yeah, exactly. You need to go to a university, not a community college. You go to a university and take an advanced statistics class, and then you learn about things like that. Something called Tukey analysis, and there are tests for that, but we don't do that in our class. We just decide whether the distribution is the same or different. Okay, and of course, we didn't say they're the same. We just said we don't have evidence to say whether they're the same or not. Any questions on this example? All right, I think I'm going to skip my next one. I had some in mind, but I'm going to go to the one after that because I want to make sure we get to everything. So here's the next example. Is there a difference in the major that men and women college graduates have? Okay, what do you think? Okay, maybe, maybe not. So if you want to find out, what you need to do is you need to do a survey. Now, I want to do a big disclaimer. Do you think I think I really did a survey and got these numbers?
No.
No, I made them up. Okay. Could a survey be done? Absolutely. Absolutely. I just didn't have time this morning to ask, hundreds of students. but it could be done. So I made it up, just let you know. So don't like, quote me on the whether that is actually true or not. But this will give you what's going on. All right. So what we want to do is we want to see, is there a difference in the major that men and women have? So now we got, notice the men's distribution of majors, and we have the women's distribution of majors, right? Do we know either of their populations? In this case, we don't know either population. Whereas in the last example, we knew the population of South Lake Tahoe. What we didn't know was the population of the college. Here, we don't know either. And if you're comparing when you don't know either, and we're comparing two different groups like this, then we're going to do what's called a chi-squared test for homogeneity. Okay, and I want to let you know on the final exam, I'm going to ask you for the name of the test you're using. So you need to have these names down. So goodness of fit is the one we just did, and this one's chi-squared test for homogeneity. And what the chi-squared test for homogeneity does is it compares two different unknown distributions. Whereas a chi-squared test for goodness of fit compares an unknown with a known. So here we don't know either, and we can still do it. Any questions on this example so far? Okay, but you can see this is done all the time, this kind of question, right? This kind of study where you're looking at, gender differences for different majors. There's a lot of different examples like that. And you'll notice the survey question is, what's your major? STEM, humanities, or other. The person's not going to say 43. The person's not going to say no. The person's going to give a word like, I'm a STEM major. Does that make sense? So this is qualitative data. And we're working on qualitative data. So be careful about seeing numbers and thinking it's quantitative. These numbers are how many people answered the different types of answers that are all qualitative. Any questions so far? Okay, then we're used to the next step, which is to write down H0 and H1. And again, we're in the chapter of wordy H0 and H1. So here, we're going to say the distributions of majors. Maybe I'll write major types. Are the same for men and women. Notice in this case, it's not distribution, it's distributions, because we have the distribution for men, distribution for women, so it's plural. So I want to highlight that because that's important. Any questions on H0? Okay, then we're going to have H1. Very simple. How does it change?
Add that not.
Yep, add the not. That's all we have to do. And I love it that I'm typing, because copy and paste is beautiful. Okay. And I think I was the first college student to be able to do this. Okay, 1984 was the year of the computer. I don't know if you realize that, but that's the year when people started having home computers. And before that, everyone used a typewriter. So I was like the first. It's kind of cool. Kind of neat to be first of a technology. You guys don't even know that like there used to be old technology, but we can actually copy and paste, which is great. Okay, any questions on H0 and H1? Okay, the good news on this one is we already have the table. Whereas with goodness of fit, we had to figure out a table. Does it make sense? But here we're given the table. So we can jump right to the calculator. So let's do that. So now I'm going to go to my calculator. And we're late in the class, which means we can scroll almost to the bottom. And guess which one it is? I hope you can all tell me.
23.
Yep, 23. So I'm going to hit 23, test for homogeneity. Okay. Do you guys know what homogeneous means? It's not a math word. It's an English word. Do you know what that word is? In fact, you know homogenized milk? That doesn't have to be human. Homogenized milk is not a bunch of people in that milk. Yeah, it's being the same. So it's being the same. It means that you're made up of the same stuff. Okay. Okay, so homogeneous means that it's the same. So it's the same distribution, whether you're men or women, basically it's the same. Okay, whereas heterogeneous or non-homogeneous is different. Okay, so that's English, not math. But those are good words to know because we're using that English. Okay, so what we're asked to do is to fill in our table. Okay, and we have A and B. And I wrote the numbers down. We have 67, 52, and 43. Oh, you know what? I missed it. I forgot the top one. 67, let's do it again. 52 and 43. And then we have 81, 118, and then we have 103. Notice the sample sizes don't have to be the same. It's not necessary to have just as many men and women in the study. Okay, any questions so far? Okay, and then we go ahead, we hit calculator. Try to make it easy. You know, I built this calculator trying to make it easy, but if you don't know what the word homogeneity is, you'll never know which calculator to use. So that's the main thing you have to know how to do. Okay, and we have our test statistic, chi-squared, is around 10, and our p-value is 0.006, rounded to 3 decimals. So what does this tell you? Yeah, we're going to get to reject the null hypothesis because we have a small p-value. Okay, again, alpha is not given, but 0.006 is lower than anything you're going to use. Okay, especially anything that is kind of more society, sociology stuff. You know, definitely not. You don't need to be that low. So let's write that out. So the chi-squared test statistic was about equal to 10. And our p-value was about equal to 0.007. Okay, which is small. Any questions so far? So what do we get to do? What's the first words?
There is significant or statistically significant evidence
And then I'm totally into copy and pasting. Oh, I don't know what happened here. That's better. Oh, I put it too high, I think. Let's see. Oh, did I not write H0 and H1? I wrote it. Where'd it go? Oh, maybe I didn't write it down yet. Let's write down H0 and H1. Sorry about that. So
You did write it down.
Yeah, I did write it down. Where is it?
Yeah. Did it get pushed down?
Oh.
Disappeared.
Yeah, it disappeared. So let's try this. Ah. Got it. Had to control Z enough times. Okay, so we had a chi-squared. Sorry about that. I have no idea what happened. Chi-squared was a 10. P-value was equal to 0.007. So the conclusion is there is statistically significant. And you can say strong if you want, because it's less than 0.01. So maybe I'll write strong. When you're really low, okay, like less than 0.01, you typically use strong. Statistically significant evidence to conclude that. And now all I have to do is copy and paste H1. And then make the T lowercase, get rid of the red. So there is strong statistically significant evidence to conclude that the distributions of major types are the same for men and women. Any questions on this? Any questions? Let me boldface the test for homogeneity, because that's probably the hardest part of this whole chapter, is to know, and let me boldface over here just to remind you. Goodness fit test. Because that's usually the hard part, is to know what test to use. So I want to let you know that that's something you have to really think about and get used to. Practice is the most important thing.
So in this case, we reject the alternate hypothesis and we accept the null hypothesis. Is that right?
I never changed the word not. I think I did Control Z on this. It was originally good. No, you never accept the null hypothesis ever in this class. Ever in stats.
Thank you.
Yeah. What I didn't do is I hit Control Z too many times and it got rid of the word not. So always good to check your work. Any questions on this? Okay, so this is a chi-squared test for homogeneity. And again, it's used a lot. And the funny thing is, what happened actually is that the book we used, the original version of the book, didn't have chi-squared test for homogeneity. I do a lot of consulting work, and test for homogeneity is like definitely in the top 2 in what people use. So I'm like, we got to have this. This is like the biggie. So I asked Barbara, she's the one that wrote the original book, and if she could put it in. You know what she told me? She said, can you write it? So that section I wrote. So I'm the author of that one little tiny piece of the book is homogeneity. and also the confidence intervals for difference between means and proportions. Those are the ones I've added in. But otherwise, I'm not the author, and I wrote all the programming and videos. Okay, so now comes the next one. All right, so is there a relationship between the type of health insurance a person has and how healthy they are? The table below shows results of a study. So private, government, and none for the type of health insurance. You could be healthy, you could have some health issues, or serious health issues. Those are the 3 different types. And then we have the table. So 55 people had private health insurance and some health issues. Any questions on the question? Okay, this is a contingency table. And by the way, it's not a coincidence that this should look a little like chapter 3. Do you know what I'm talking about? And exam 1. I know it's been a while, but the final's not that many weeks from now, so you do need to remember that stuff. Do you remember doing this? Yeah, and in fact, we actually tested to look to say, is government and having some health issues, are they independent? Do you remember that? So what we want to find out is not government versus some health issues. We want to look at health insurance versus health, how healthy someone is, overall being independent or dependent. Any questions on that? Whereas in chapter 3, we looked at one specific cell and decided whether what corresponded to that cell were those independent. But here we're looking at overall independence. So we're going to be doing a test for independence. And it's chi-squared again. So that's going to be a chi-squared test for independence. Let's boldface it. And I want to mention something else, that sample sizes. How do you decide if the sample size is large enough? Any guess?
Wouldn't you add, I mean, you could see that the sample size is pretty big, adding each individual, right? 76, 59, 48. That's
okay. So let me tell you something. Have this 30 been a 3? I haven't changed the overall sample size much, have I? And actually now it's no longer large enough. Now it's large enough. So you got to be careful about looking overall. It turns out what you need all of what's called the expected numbers to be greater than 5. And we've learned about greater than 5 for qualitative before, when it was yes, no. Now it's just regular qualitative, it's still greater than 5. Okay. So the expected values, which are not that far from what the observed values are, I think I'm not going to go over the mathematics for that because you're not required, but just the idea is that if one of them is really tiny, what you would expect, then that's not okay. Okay, really tiny means 5 or less. So you got to make sure that all of your counts are big enough, and that's the same as the other tests we've done also, is you have to make sure the expected values are bigger than 5 for all of them. Okay, not just any individual or overall sample size. Overall sample size doesn't matter. What matters is the individual expected numbers. So we're going to use what's called a chi-squared test for independence. And at this point, you better all be used to the fact you should write H naught and H1 now. And H naught is going to be that type of health insurance. and how healthy a person is, are independent.
Do we not need the word distribution in this one?
In fact, you can't have the word distribution. It has nothing to do with
Okay.
distribution. So it's a good question because you don't want to make that mistakes. But notice I just highlighted. If you don't have the word independent, I will take off points. Okay, and note that independent is very important. Independent is the H naught. Okay, H1 will not have the word independent. So independent is H naught. Then let's write down H1. I'll copy and paste. Make it an H1. And that's type of health insurance and how healthy a person is are, what's the opposite of independent?
Dependent.
Dependent. So H1 has the word dependent. And that's it. There's our H naught, there's our H1. Any questions at all on this particular example and H naught and H1? Okay, very much formulaic. I mean, you just go through, not every problem is going to be about type of health insurance, let you know that. But whatever the two things are, you write down they're independent for H naught, and you write down they're dependent for H1. Any questions on that? Okay, so next thing we got to do is we need to find the p-value. So let's go find the p-value. To do that, obviously, we go to a calculator. And this should be really obvious. Which one? Yes, this is 22. Okay, so the hard part is not choosing, after writing down the hypotheses. The hard part is deciding whether it's a test for independence at the very beginning. Once you know that, you'll know what calculator to go to, but you have to know that. Okay, so here we go. We have our table had 76, 55, 42, and then 59, 63, 40, and then 48, 41, and 30. Any questions on filling in the table? And I want to let you know that whether you read it rows or columns doesn't make any difference. So if I wrote 76, 55, 42 as a first column, and did it by columns, that still works. So it doesn't really matter, which one you do, as long as you're consistent. Then I'm going to scroll, hit calculate. My chi-squared is 2.4. My p-value is about 0.66. So what's the solution? And what do we say?
What was the p-value? Sorry, I was writing it down. And
You see it?
yeah, we would fail to reject.
Yeah, so we fail to reject. So that means there is
Not statistically significant evidence.
or statistically insignificant
Yeah.
evidence to decide whether or not, and now I can copy and paste, type of health insurance and how healthy a person. I could pick either of these for whether or not. Doesn't really make a difference. If the p-value is small, you pick H1.
Thank you.
So there is statistically insignificant evidence to decide whether or not type of health insurance and how healthy a person is are independent. Or you can write dependent, doesn't matter as long as when you have a high p-value. If you have a low p-value, it's you know that they're dependent. Any questions at all on the test for independence? Notice this is also a qualitative survey question, right? What kind of health insurance do you have? You don't say 73 or no. You say private, government, or none are the three choices. Any questions at all on this example? Okay, I don't know if I'll do the full out example, but I have some other examples to look at that they come up with. So let's look at this next one. Is income normally distributed in the United States? What do you think? Do you think the distribution of income in the US is a normal distribution curve? Any thoughts? Okay, well, how would you find out? Okay, because we've talked about, remember we assume normal, which is always a bad thing. So there are actually ways of testing to decide if it's normal, and here's one of them. So a survey was done, and then the z-score was calculated for each respondent. Okay, which you know how to do, by the way, I hope, is that if you have a bunch of data, you know how to find the z-score of each number, right? You find the means, find the standard deviation, and then you do x minus mu over sigma. And that gives you z-scores. And what we found is that of the 1,000 workers that were looked at, 58 had a z-score under -2, 190 had a z-score between -2 and -1, 321 had a z-score between -1 and 1, 345 had a z-score between 1 and 2, and 86 had a z-score greater than 2. So the big question I have here is, what kind of test is this? I'm not going to do the full thing because we don't have so much time, but I want you to be able to recognize what test to use. Any thoughts? I don't see y'all jumping in. Okay, so we want to find out whether this population that we don't know about has a normal distribution. Does that help at all or not? Okay, if you don't know, let me write it down. Yeah? Stephanie Chi-Square?
Would it be goodness of fit test?
Yeah,
sorry.
goodness of fit. Because we know the normal distribution. We know everything about the normal distribution. We don't know is the distribution of income in the United States. So it's a goodness of fit test. And in fact, let's just do this part. I don't want to do the whole thing because I don't want to spend all day. Is how do you get the expecteds? Let's start here, I think is easiest. Between -1 and 1, what's the expected count? Okay, and if you remember the empirical rule, 68% of a normal distribution should have between -1 and 1 for the z-score. Do you remember that? That was part of the empirical rule, that 68%. And 68% of 1,000 is 680. 1,000 workers. Okay, any questions on that? Okay, 2.5% are going to be in this very low area. 2.5% of 1,000 is 25. And it's symmetrical, so it's going to be 25 here also, above 2. And that way, 25 plus 25 is 50. 50 is 5% of 1,000. Okay. If we want to find out these last two guys, well, we have symmetry. So they should be the same number. And we already have what? 680 and 50 more is 730. So there's 270 left. Half of that is 135. So they're each 135. Any questions on that? And then we go ahead and do a good as a fit test. Okay, which hopefully you're okay if I say you know how to do it at this point. It's just like the first one we did. Okay, the hard part for most people would be getting these numbers and actually identifying goodness fit, that that's what you have to use, and then getting the expected counts. Any questions on this? Okay, and by the way, our H naught, again, I'm not going to do the whole test, but at least I should write down H naught. H naught is the distribution. Remember, the word distribution has to be there. What was the calculation for 680? Okay, so the empirical rule says 68% is within 1 standard deviation of the mean. Do you remember that? And 68% of 1,000 is 680. Does that help? Okay, so the distribution of income in the US is normal. And then H1, the distribution of income in the US is not normal. That's it. Okay. Any questions on this example? Any questions? Let me just go over the last example. If I can find it. Here we go. Okay, so here's another question. Does color of the wrapper matter when it comes to whether a shopper will buy candy? Okay, so again, you might own a candy shop and you have to decide, well, do you want to wrap your candy in blue? Do you want to wrap your candy in pink? Do you want to wrap your candy in green, etc.? Does that make sense? So what you might do is try them all, see what happens. So a candy shop experimented by selling candy in blue, pink, orange, and green wrappers and seeing what customers bought. Okay, maybe the prices were all the same and seeing what people grabbed. Sound good? The store ended up selling 37 blue wrappers, 49 pink wrappers, 14 orange wrappers, and 20 green wrappers. Okay. And what can be concluded? So the question I have for you is, what kind of test? Scroll up. I'm not sure if that's the up you want. A little more, really? Okay. So what kind of wrappers, what kind of test? So what do you think? Yeah, this one's goodness of fit also, because we just have the sample that we don't know. We don't know its distribution. We want to see if it is, in one word. So first, goodness fit. The distribution of color purchases It's what? I'm looking for a word. Not different. The word we had pretty much a whole chapter on this word. All right, if I don't see y'all jumping in, uniform. Because uniform means all the same. Remember that? Same probability for every different possibility. Okay, and it's a discrete uniform in this case. And H1 is the distribution of color purchases is not uniform. And that's it. I don't think I need to go through another goodness of fit, but just to give you an idea that a lot of times the hard part is deciding what the null alternative hypotheses are and what the test that you have to use is. I don't know if you agree, but that's what, and especially because again, we're in this chapter where it's just these three. On the final exam, how many tests do you think we have so far? And we're going to have more, by the way, a couple more. We have a lot of different hypothesis tests and confidence intervals too, right? So one of the hardest parts in the final is to decide what to do, how to start. If you don't know how to start, you have no chance of doing anything. Because if you start wrong, if I ask you to do this problem and you try and do some kind of test for difference between two means, it's not going well for you. If you don't know to do goodness of fit, you have no chance. So that is really, really important.
How would you just, I mean, I know that we apparently didn't know about the uniform word. So would you decide on using the purchases as uniform by seeing if the wrapper cells kind of have like go into that bell shape, or who purchases
not bell shape, bell shape normal.
The 37 blue.
Yeah, the uniform shape. Rectangle, right? So the idea here is that if it doesn't matter what wrapper, that means the percentages should all be the same.
Okay.
You see? And all the same, that's the word for that is uniform. And that you are responsible for knowing that. That's what uniform means, right? And in fact, that's when you think of uniform, right? That's something you wear in the military or, in some private schools. And that's because everyone should look the same. So we don't, play favorites. I don't know if you realize that that's the reason, but that's why we call it uniform, is for everyone to look the same. Okay, so we use that word. My guess is military got to it before stats, but we use it. I don't think the military borrowed it from statisticians. I think the other way around. Yeah, so that has to do with the fact if all the same, that's uniform. The main, we haven't had that many distributions in the class, and basically uniform, we've had normal, and a few others, but those are the uniform and normal are the two we actually have good descriptions of the shape, right? So it's not like you have a lot of choices. Okay, let me show you, which I actually did earlier. I don't know if anyone noticed. The secret word. And the secret word for this week is distributions. Notice it's plural because I'm thinking homogeneity on this one. And that's a word that, make sure you put in with homogeneity. If it's not homogeneity, then it would be without the S. But for the secret word, it's distributions. So we've now seen all the main tests for this class. I want to let you know, you do have the homework on chapter 11. Okay, there is this week there is a discussion post because it's not like you're taking an exam, although there's a project due. But the project is going to be the hardest part of the week. Okay. The homework assignment is not that bad, but the project is long. So make sure it's, difficult. Make sure that you work on the project. What words must be in your project over and over and over again?
Margin of error.
Margin of error could be a couple times,
Yeah.
but over and over and over and over again throughout the whole paper. Standard error is going to be a whole paragraph. but
Standard
not-
error.
Those are some words, but population mean.
Okay.
So, and you're going to, because the whole project is about comparing two population means. So those words need to be in everywhere. Every time you're describing anything, you're going to be describing population means. Does that make sense? So don't forget standard error. Standard error is in definitely a bunch of places, but population mean is like, I'd say most sentences are going to have those words. So that is important to keep that in mind. It's all about the population mean. And don't forget, it's all about talking about what your client is going to make, what decision your client is going to make based on everything. So a whole sentence on what decision is the client going to make based on the lower bound for the confidence interval. A whole sentence based on the upper bound for the confidence interval. A whole sentence based on the standard error. A whole sentence based on the p-value. A whole sentence based on the level of significance versus the p-value, right? You know, and possibly more than one sentence. So it's all about the client. Okay, don't just define anything. Defining doesn't help at all. It's about what the client is going to do with that information. And note that a confidence interval talks about how much bigger one is than the other, whereas a hypothesis test is one bigger than the other. They're very different. Confidence intervals actually give more information. So I want to kind of give you some of the main things to think about as you're writing, because pretty soon you should be writing that paper. Any questions at all about anything?
I have a question on the project just because we're
I think I'm
we
going
finally
to
just got
kill the recording because we're in Q&A time.
okay.
So
Okay.